Bismillah ar-Rahman ar-Rahim. This video is about the eigenstructure of the unitary DFT matrix, specifically the multiplicity of its eigenvalues. We have a discrete time signal with samples x of 0, x of 1, all the way to x of big N minus 1. The unitary DFT of these samples is x of k, where k is an integer from 0 all the way to n minus 1. X of k is the summation n from 0 to big N minus 1. X of n we multiply here by e to the minus I 2 pi kn over big N. And here we have the vector 1 over square root n. This is the unitary DFT. We can think of the input signal, small x, as an n-dimensional vector in the n-dimensional complex space. The components of this vector are small x of 0, small x of 1 to small x of big N minus 1. The unitary DFT signal big X of k can also be thought of as an n-dimensional vector. This vector big X in Cn, and its components are big X of 0, big X of 1 to big X of n minus 1. We can think of this summation here as a linear transformation of that vector, a matrix that is multiplied by that vector from the left to yield that vector big X. We can write down big X, which is the DFT of small x, as F, this is the unitary DFT matrix, times small x. This matrix here, it has this factor 1 over square root n, but what are the elements of the matrix? Here is vector big X, and this is the factor 1 over square root n, and then we have our matrix, and this is the vector small x. What should this matrix be? If k is equal to 0, then this exponential is equal to 1, and big X of 0 is the sum of those samples in this vector here divided by square root n. So the topmost row in this matrix is a row vector of 1s. Every sample here is multiplied by 1. We sum them, divide by square root n. This will be big X of 0. If k is equal to 1, let's see. We have big X of 1 is equal to 1 over square root n, summation n from 0 to big N minus 1, x of n, e to the minus I 2 pi small n over big N. If small n is equal to 0, this is 1, and x of 0 is multiplied by 1. So we have a 1 here. Now, if small n is 1, then x of 1 is multiplied by e to the minus I 2 pi over n. Then x of 2 is multiplied by e to the minus I 2 pi over n. And then we have a 2, because n is equal to 2. And this continues. X of n minus 1 is multiplied by e to the minus I 2 pi over big N, and then we have n minus 1. If we denote e to the minus I 2 pi over n by omega, then this second row here is 1 followed by omega, then omega squared, omega cubed, all the way to omega big N minus 1. What about big X of 2? Big X of 2 is 1 over square root n, and then x of 0 is always multiplied by 1, because when small n is equal to 0, this exponential is 1. And then now case 2, so x of 1 is multiplied by e to the minus I 2 pi n, and then we have a 2 here. X of 2 is multiplied, so now k is 2 and n is 2, then this will be e to the minus I 2 pi over n, and then we have 4, and so on. Using omega, the second row is 1, and then omega squared, and then omega to the 4, and then omega to the 6, all the way to omega to the 2n minus 1. We can continue the construction of this matrix. This is the unitary DFT matrix, and I keep saying unitary, as we will check now. This matrix is a unitary matrix. F Hermitian F is equal to F Hermitian is equal to identity of size big N by big N, which means that the inverse of this matrix is its Hermitian. The unitary DFT, or sometimes I will just say the DFT, is to take this vector small x with the samples from x of 0 to x of n minus 1, multiply this vector from the left by this matrix here. This seems like an interesting matrix, so let's study some of its properties. This matrix F is symmetric, which means that F of kV is equal to F of Vk. This is 1 over square root n e to the minus I 2 pi over n kV. As is clear from here, interchanging k and v will not change this element in the matrix. Let's examine the inner product of the kth and dth columns. K and v are in the set from 0 to n minus 1. The kth column, 1 over square root n, then 1 omega to the k, omega to the 2k, and so on. The vth column, 1 over square root n, 1 omega to the v, omega to the 2v, and so on. These two guys will give us the 1 over n. We need a summation n from 0 to n minus 1, and then we need to take omega to the nv from here and multiply by the complex conjugate of the corresponding element in this vector. And so this will be omega to the minus nk. Note that when we take the complex conjugate, we just change the sign here. This is the summation that we have. If k is equal to v, then we have e to the power 0, that's 1. The summation is n, and n divided by n is 1. This means that each column in matrix F has a unity L2 norm. What if V is not equal to K? In this case, we can take this summation and we can write it as a geometric series, e to the minus I 2 pi over n V minus K, and then all to the power n. What is this summation? We have 1 minus the ratio of the geometric series to the power of the number of terms, which is big N. This will give us in the numerator 1 minus exponential minus I 2 pi over big N, and then V minus K, and then times N. So we can eliminate this N here. In the denominator, we have 1 minus the ratio exponential minus I 2 pi over big N V minus K. Let's examine the denominator. Now, V minus K is not 0 because V is not equal to K. And V minus K cannot be equal to big N or minus big N. And this is because of the range of those guys here. The maximum positive value of V minus K is big N minus 1. And the least negative value is minus between brackets big N minus 1. In other words, that this V minus K here cannot be a multiple of big N. This exponential is not equal to 1. And we have a non-zero quantity in the denominator. Upstairs here, we have exponential minus I 2 pi times an integer. That's 1. 1 minus 1 is 0. So we have 0 in the numerator and a non-zero quantity in the denominator. That's 0. If V is not equal to K, we have 0. Which means that if we talk about two distinct columns from the unitary DFT matrix F, then the inner product is equal to 0. Any two distinct columns in the matrix are orthogonal to one another. And this is exactly what we mean when we say that F is a unitary matrix. Each column in the matrix has a unity L2 norm, and the columns are orthogonal to each other. Now, we want to examine the powers of the DFT matrix F. What is F squared? What is F cubed? What is F to the power 4? What is F squared of X? We can think of this as F applied to F of X. So we have X, and then F times X, that's the unitary DFT of small x. Now, if we multiply by F again, then we are taking the DFT of the DFT. We can understand what F squared is by examining or answering this question. What happens if we take the DFT of the DFT? Now, the DFT of X of n, that's X of K. What does it mean that we take its DFT? So here is X of K. By the definition of the DFT, we need the summation, and then K, the index, goes from 0 to big N minus 1. We need to multiply by e to the minus I 2 pi K, which is this index here, and then we have the index of the output, let's call it m, and then we divide by the number of terms in the sum, which is big N, and then we have the scaling factor, which is 1 over square root n. This is the DFT of the DFT. X of K itself is 1 over square root n, and then the summation. We have a double sum. We can interchange the order. So we have the summation with respect to n first, small n from 0 to big N minus 1, and then we have X of n, and then these two guys give us 1 over big N, and then we have a summation. We combine these two exponentials, we have e to the minus I 2 pi K, and then n plus m over big N. Now, this summation resembles what we have here. If m is equal to 0, and if small n is not equal to 0, in this case, n plus m is not a multiple of big N. And using the same argument like here, this is a geometric series that is equal to 0. But if small n is equal to 0, then this summation here will be the sum of ones. 1 added to itself big N times, that's n. N divided by n, that's 1. And so the result of this double sum, when small m is equal to 0, is x of 0. We have n terms again, but only one term. Only one of those small x values will be multiplied by 1. The others will be multiplied by 0. The result is x of 0. Now, if small m is in the set from 1 to big N minus 1, then we have a similar situation. From this summation of n terms, only one term, only one of those small x values will be multiplied by 1. And the other terms will be multiplied by 0. Specifically, if small m is any value in this set here, then the surviving term is the term where small n plus m will give us big N. Okay, so n is big N minus m. This will be the surviving term, and the output, the result, is x of big N minus m. This is the DFT of the DFT. So if we have vector x, x of 0, x of 1, x of 2, x of 3, and then x of big N minus 2, x of big N minus 1. Then what is the result of taking or applying the discrete Fourier transform twice? The first output is small x of 0. This means that F squared as a matrix, the topmost row has a 1 here followed by zeros, so that the first output is small x of 0. What is the next output? If small m is equal to 1, then the output is small x at big N minus 1. So the next row that we have below the topmost row should have 1 as the last element, and then the other entries in the row should be 0. Then to obtain the next output, we should have a 1 here to be multiplied by x of n minus 2, and then the remaining elements in the row are 0, and so on. This is F squared. As we can see, matrix F squared is a real valued matrix. We have 1 here, and then we have an identity matrix of size n minus 1 by n minus 1 that is flipped left, right. So it looks like this. This is f squared. What about f cubed? And the investigation of f cubed is equivalent to asking the following question. What is the result of applying the discrete Fourier transform 3 times in a row to samples from x of 0 to x of big N minus 1? What is the DFT of the DFT of the DFT? We take our result here, let's call it z of m, and what we do is we have a summation m from 0 to big N minus 1, z of m, and then e to the minus I 2 pi m, and let's say that to index the output we will use v, and then we have over big N, and the scaling factor 1 over square root n. This is the DFT of the DFT of the DFT. Now, when small m is equal to 0, z of 0 is small x of 0, and it is multiplied by 1. This is this term here. And then we have the sum when small m is from 1 to big N minus 1. Z of m is x of big N minus m multiplied by this exponential here. Let's do the following change of summation index. We have small l is equal to big N minus small m. When small m is 1, small l is big N minus 1. When small m is big N minus 1, then small l is equal to 1. So the index l is also from 1 to big N minus 1. Now x of big N minus m becomes x of l. And this m here must be changed to big N minus l. If we look at this exponential, it can be written as e to the minus I 2 pi big N over big N v, and then e to the I 2 pi L v over big N. This is equal to 1. So the exponential here looks like the exponential that appears in the definition of the unitary DFT, but here we have a plus sign. This is what we have. In other words, if we apply the DFT 3 times in a row to the signal x of n, we get vector x multiplied by the conjugate of the unitary DFT matrix. Recall that the DFT matrix is symmetric. F is equal to F transpose. When we apply the DFT 3 times, F cubed is equal to F conjugate, and F conjugate is F transpose conjugate. If we transpose and then take the complex conjugate, this is F Hermitian. F cubed is equal to the Hermitian of the unitary DFT matrix. Applying the discrete Fourier transform 4 times, this is like multiplying vector x by f to the 4. This is f to the 3 times f of x, but f to the 3 is f Hermitian, and f Hermitian times f is equal to identity. It means that f to the power 4 is exactly the identity matrix. If lambda and q is an eigenpair of f, fq is equal to lambda q. If we multiply both sides from the left by f, we get that f squared q is equal to lambda fq, but this is lambda q. So this right-hand side is lambda squared q. If we multiply by f again, we get f cubed q, and then we have lambda squared fq, and fq is lambda q, so I can put this lambda to the power 3 and then q. Finally, if we multiply by f from the left again, then we get f to the 4q, and this is lambda 3 fq, which is lambda q. That's lambda to the 4q. But f to the 4 is the identity matrix, so this is equal to q. Lambda to the 4 times this non-zero vector q is equal to q. Then lambda to the 4 is equal to 1. Lambda is an eigenvalue of f. Lambda satisfies the equation that lambda to the power 4 is exactly equal to 1. This means that the possible eigenvalues of the unitary DFT matrix are the solutions to this quartic polynomial equation, plus 1 or minus 1 plus I or minus I. The question now is about the multiplicity of each of these eigenvalues. In other words, in the general case, when matrix F is n by n, how many of its n eigenvalues are equal to plus 1? How many are equal to minus 1? How many are equal to plus I? And how many are equal to minus I? Consider the matrix G. 1/4 times this sum, identity plus f squared plus f cubed. What is the Hermitian of matrix G? Note that identity and f squared are symmetric real-valued matrices. So the Hermitian of these guys, I and f squared, is I plus f squared. Note that f cubed is equal to f Hermitian. So the Hermitian of f is f Hermitian, which is f cubed, and the Hermitian of f cubed, which is f Hermitian, is f. Then G Hermitian is exactly equal to G. Let's examine G squared. G squared can be written as G Hermitian G because it is a Hermitian matrix. G is 1/4, and then we have the sum I plus f squared plus f cubed, and G Hermitian is 1/4, and let's write it in this way. Identity, then G has f cubed, which is f Hermitian, so the Hermitian of f cubed is f, and then we have the Hermitian of f is f Hermitian, and the Hermitian of f squared is f squared. Let's expand identity times those 4 matrices, we get them back, and then when we multiply by f, we will get f, and then f squared, and then f cubed, and then f to the power 4, which is identity. The same 4 terms like here. If we multiply by f Hermitian times identity, that's f Hermitian, which is f cubed. F Hermitian times F, that's identity, because F Hermitian is the inverse of F. F is a unitary matrix. F Hermitian times F squared, that's F, and F Hermitian times F cubed, that's F squared. Again, the same four terms. Lastly, if we multiply by F squared, we get F squared, F cubed, and then F to the power 4, which is identity, and then F to the power 5, which is F times F to the power 4, which is F. So these four matrices appear 4 times, and the result for squaring matrix G is 1/4, and then the sum again. That's G. G is an idempotent matrix. G is a projector or a projection matrix, and because it is Hermitian, it is specifically an orthogonal projection matrix that takes a vector in the n-dimensional complex space and projects it orthogonally onto its range or column space. Note that G is idempotent, so its eigenvalues satisfy the equation that lambda squared is equal to lambda. The eigenvalues of G are either 0 or 1. The rank of G, which is the dimension of its column space or range, is the trace of G. Why is this? Suppose that we sum the algebraic multiplicities of the eigenvalues of a matrix. This summation is equal to n, the size of the matrix. So those are the eigenvalues of an n by n matrix. Now let's separate this summation into summation with the eigenvalues that are non-zero. And here we will write n minus the algebraic multiplicity of the eigenvalue 0, if the matrix has an eigenvalue of 0. We have a rule that for any eigenvalue, the algebraic multiplicity is greater than or equal to the geometric multiplicity. So we can upper bound this right-hand side by n minus the geometric multiplicity of 0. Recall that the geometric multiplicity of eigenvalue lambda is the dimension of the null space of the matrix if the matrix is called A minus lambda times identity. If we are interested in the eigenvalue 0, then the geometric multiplicity of 0 is the dimension of the null space. This is equal to n minus the dimension of the null space of the matrix. Let's say that the matrix is A. Now from the rank nullity theorem, we have that the number of columns of the matrix minus the dimension of its null space, this is exactly the rank of the matrix, rank of A. The rank of the matrix is greater than or equal to the sum of the algebraic multiplicities of its non-zero eigenvalues. Note that the only inequality involved is this inequality, in which we said that for any eigenvalue, the algebraic multiplicity is superior to or is equal to the geometric multiplicity of the eigenvalue. Thus, the rank of the matrix is equal to the sum of the algebraic multiplicities of its non-zero eigenvalues if the algebraic multiplicity of 0 is equal to the geometric multiplicity of 0. And so for diagonalizable matrices, like for example projection matrices and unitary matrices, for all those matrices that are diagonalizable, the algebraic multiplicity of any eigenvalue is equal to the geometric multiplicity. In this case, any diagonalizable matrix, we have that the rank of the matrix is the sum of the algebraic multiplicities of its non-zero eigenvalues. Let's apply this idea here. G is a projection matrix. Matrix G has eigenvalues that are 0 or 1. And according to this rule here, the rank of G, the dimension of its range, is the algebraic multiplicity of the eigenvalue 1. We need to count how many times the eigenvalue 1 appears when we take the characteristic polynomial of G and equate it to 0. Since the trace of the matrix is the sum of its eigenvalues, then when we compute the trace of G, we simply count how many times 1 appears as an eigenvalue. So because G is idempotent, and because we have this rule here, then the rank of G is the trace of G. And this will be our way to obtain the algebraic multiplicity of the eigenvalue 1 of the unitary DFT matrix. Suppose that Q is one of the eigenvectors of the unitary DFT matrix associated with eigenvalue lambda equal to 1. Fq is equal to 1 times Q, and F squared Q is equal to Q, and F cubed Q is equal to Q. If we apply G to Q, if we multiply Q from the left by G, G is 1/4, and then we have this sum. Now identity times Q is Q, F times Q is Q, because Q is an eigenvector of F associated with the eigenvalue 1. F squared Q is Q, F cubed Q is Q. So this bracket times Q is 4Q divided by 4, that's Q. So we have GQ is equal to Q. Q is an eigenvector of G, and the associated eigenvalue is equal to 1. But what if we multiply G by an eigenvector of F that is associated with the other eigenvalues, -1 or plus I or minus I? Q1 is an eigenvector of F associated with the eigenvalue -1. Fq1 is equal to minus Q1. If we multiply by F, then F squared Q1 is minus Fq1. But Fq1 is equal to minus Q1. So F squared Q1 is Q1. If we multiply by F again, we get minus Q1. And if we multiply again by F, we get F to the 4th. That's identity, and so we should get Q1. Now let's investigate GQ1. Identity times Q1, this will give us Q1. F times Q1, this will give us minus Q1. F squared times Q1, this will give us Q1. F cubed times Q1, this will give us minus Q1. That's 0, which means that an eigenvector of F associated with the eigenvalue -1, this will result in GQ1 is equal to 0Q1. It's an eigenvector of G associated with the eigenvalue 0. Recall that F has the eigenvalues 1, -1, I and minus I. G, which is constructed from F using this. G, on the other hand, is an orthogonal projection matrix. It's Hermitian, idempotent. Its eigenvalues are either 0 or 1. So far, we have shown that if there is an eigenvector of F associated with the eigenvalue 1, then it is an eigenvector of G associated with the eigenvalue 1. But when we tried to study G times an eigenvector of F associated with the eigenvalue minus 1, what we obtained is that this is an eigenvector of G, but it is associated with the eigenvalue 0. The same conclusion holds if we study Q2, which is associated with I, or Q3, which is associated with minus I. For example, if Q2 is equal to I Q2, if you multiply by F again, this will be F squared Q2 is equal to I F Q2, and this is equal to I Q2, so we get minus Q2. And then F cubed Q2 is minus I Q2, and F to the 4 Q2 is equal to Q2. Now, if we take these and examine G times Q2, we will get I Q2 minus Q2 minus I Q2 plus Q2, and this is equal to 0 Q2. And the same will happen if we examine Q3, which is an eigenvector of F associated with the eigenvalue minus I. Suppose that beta is in the range of matrix G. G beta is equal to 1 times beta. Beta is an eigenvector of G associated with the eigenvalue 1. Now, write down G as the sum 1/4 of I plus F squared plus F cubed. Take F as a common factor to the left. So we have here 1/4, and then we have F in the bracket. To get I, we need here the inverse of F, which is F Hermitian. Then we need identity, then we need F, then we need F squared. And F Hermitian is exactly F cubed. So this bracket is 4 times G. What we have is Fg times beta is equal to beta. But G beta is beta, so F beta is equal to beta. What have we done here? We started with a vector in the range of G, an eigenvector of G associated with the unity eigenvalue. We discovered that it is also an eigenvector of F associated with the unity eigenvalue. Now, it is clear that the range of G is exactly the eigenspace associated with the unity eigenvalue of the unitary DFT matrix F. We can find the algebraic and the geometric multiplicity of the unity eigenvalue of the DFT matrix by obtaining the rank or the dimension of the range of G. And this is equal to the trace of G. So the algebraic multiplicity of the unity eigenvalue of the unitary DFT matrix, this is equal to 1/4 the trace of identity plus F squared plus F cubed, which is F Hermitian. What is the trace of identity? That's n. The sum of the elements on the main diagonal, that's n. What about F squared? Recall the matrix F squared. It's a symmetric real valued matrix. It has 1 here, and then you take identity and flip it left, right, like this. If big N is equal to 1, then the trace is 1. If big N is equal to 2, then we have identity and the trace is 2. What if big N is equal to 3? In this case, we have the trace is equal to 1. And if N is equal to 4, now the trace is equal to 2, and so forth. The trace of F squared is 1 if big N is odd. The trace of F squared is 2 if big N is even. Lastly, we have F plus F cubed, which is F plus F Hermitian. This is the trace of F plus the trace of F conjugated. This is double the real part of the trace of F, or F Hermitian. Okay, so we can compute the trace of F or the trace of F Hermitian. Take the real part, multiply by 2, and this will be the trace of F plus F cubed or F plus F Hermitian. What are the main diagonal elements of the DFT matrix, or the Hermitian of the DFT matrix? Those are elements in the form e to the I 2 pi over n, and then j times j squared, where j is 0 or 1 all the way to n minus 1. The trace specifically is the sum of those guys over square root n. This is the Gaussian sum done in a previous video, and it is equal to 1/2 square root n times 1 plus I times 1 plus I to the minus big N. If n is divisible by 4, then I to the power minus n is equal to 1. And what we have here is square root n times 1 plus I. The real part is square root n. We multiply by 2, divide by square root n, we get 2. If n is 1 mod 4, then this is 1 minus I. 1 plus I times 1 minus I, that's 2. 2 goes with 2, and we are left with square root n. Times 2 over square root n, that's 2 again. If big N is 0 or 1 modulo 4, then the result here is equal to 2. If n is 2 mod 4, this I to the minus n is minus 1. Thus, this bracket is equal to 0, and we get 0. Finally, if n is congruent to 3 mod 4, I to the minus n is equal to I. then this is 1 plus I squared. This is equal to 2I. The result is purely imaginary, and so the real part is equal to 0. This quantity of interest is 2 if n is congruent to 0 or 1 modulo 4 is equal to 0 if n is congruent to 2 or 3 modulo 4. Now we combine our results. Matrix G is 1/4. Then we have identity plus f squared plus f Hermitian. From identity, we get here n. For f squared, the trace is 1 if big N is odd. So the trace of f squared is 1 if big N is congruent to 1 or 3 mod 4. The trace is 2 if n is congruent to 0 or 2 mod 4. For f plus f Hermitian, the trace is 2 if n is congruent to 0 or 1 modulo 4 and is congruent to 0 if n is congruent to 2 or 3 modulo 4. Combining these results, this is the trace of G, and this is the algebraic multiplicity of the eigenvalue 1 for the unitary DFT matrix. What about the other eigenvalues? -1, I, and -I. The idea is exactly the same. The trick is to come up with something like matrix G, such that the matrix is an orthogonal projection matrix with a range or column space that coincides with the eigenspace of interest of the unitary DFT matrix. To be concrete, suppose that we want to repeat this exercise for the eigenvalue I. In that case, we will construct matrix G. Let's call it G with the subscript I. What should be Gi for our purposes? I claim that it should be 1/4, and then we have the sum of 4 matrices. Those 4 matrices are identity minus I times the unitary DFT matrix F minus F squared, and then we add I times F cubed. Let's do our checks. Suppose that I have this matrix. Is it a Hermitian matrix? Gi Hermitian. This is 1/4. Hermitian of identity is identity. We are taking the Hermitian of this guy. Minus I becomes plus I. And F becomes F Hermitian. And F Hermitian is the same as F cubed. F squared is symmetric and real valued. Its Hermitian is itself. Plus I becomes minus I. And F cubed is F Hermitian. When we take Hermitian, that's F. We get back Gi. So Gi is indeed a Hermitian matrix. Is it idempotent? What will happen if I take Gi squared? And we can check that it is indeed idempotent. It is a projection matrix, and because it is Hermitian, it is an orthogonal projection matrix. Its eigenvalues are 0 or 1. Suppose that Q is an eigenvector of F associated with the eigenvalue I, so Fq is equal to IQ. Now, what will happen if we multiply Q from the left by this matrix Gi? We have 1/4. Let's see. Identity times Q, that's Q. Minus IF minus I, and F times Q is I times Q. So we have IQ, and this becomes plus Q. Then we have minus F squared Q. Now, if we multiply here by minus F, we will get that minus F squared Q is minus IFQ. And FQ is equal to IQ, I times minus I, that's 1. So minus F squared Q is also equal to Q. If we multiply both sides here by minus F, we get F cubed Q is equal to minus FQ. And minus FQ is equal to minus IQ. And there is an I here, so that's plus I times minus IQ, that's Q. We get 4Q divided by 4. Then this is Q. In other words, that if Q is an eigenvector of F associated with the eigenvalue I, then Q is an eigenvector of Gi associated with the unity eigenvalue. Now, what will happen if I take a vector, let's say beta, such that Gi beta is equal to beta? That's a vector in the range of Gi. Write Gi as a sum, so this is 1/4, and then we have identity plus I, F cubed minus F squared minus IF times beta is equal to beta. Take F as a common factor to the left. We need to get identity, so here we put the inverse, which is F Hermitian, or we can write it as F cubed plus I. And then here we have F cubed, so we need here F squared. And then we have minus F squared, so I need to put minus F, and then minus I times identity. Now take the scalar minus I as a common factor. So this is minus I over 4F. We have here IF cubed, then minus F squared, minus IF. Finally, we have plus identity. This matrix is exactly matrix Gi when we include this 1/4. What we have is minus IF G sub I times beta is equal to beta. Multiply both sides by I. Then F Gi beta is equal to I beta. Gi beta is equal to beta. Then F beta is equal to I beta. If we take any vector in the column space of G sub I, then this vector here is in the eigenspace associated with the eigenvalue I of the unitary DFT matrix. If we are interested in knowing the multiplicity of this eigenvalue I, then the way to go is simply to find the rank or the dimension of the range of GI. Because I is a projector and it has just 0 and unity eigenvalues, we obtain the rank by taking the trace. So the algebraic multiplicity of I will be the trace of this matrix G sub I. We need to compute this trace. Let's remind ourselves, we have 1/4 and we have the 4 guys are I, and then we have I f cubed, which I can write as f Hermitian minus f squared minus I f. Trace of I, that's always equal to big N. The trace of minus f squared, okay, so this is -1 or -2. This is -1 if big N is congruent to 1 or 3 modulo 4. And this is -2 when we take the trace if big N is congruent to 2 or 0 mod 4. In other words, if big N is even. Then we have now the trace of I f Hermitian minus I f. So this is I, the trace of f Hermitian minus f. This is the trace of f Hermitian minus the trace of f Hermitian conjugate. F Hermitian minus the trace of f Hermitian conjugate. Okay. And if we have a complex quantity minus its complex conjugate, then what we get is double the imaginary part times I. This is -2, the imaginary part of the trace of f Hermitian. And so this is -2 divided by square root n. And we have the imaginary part of the Gaussian sum, summation j from 0 to big N minus 1 e to the I 2 pi over n j squared. This is equal to minus the imaginary part of 1 plus I times 1 plus I to the minus n. Let's do the cases. If n is divisible by 4, then I to the minus n is 1, that's 2. And so the imaginary part is -2. If n is congruent to 1 mod 4, in this case, I to the minus n is minus I, 1 plus I times 1 minus I, that's purely real, and the imaginary part is 0. If big N is congruent to 2 mod 4, then I to the minus n is -1, and 1 plus -1, that's 0, we get 0 again. Finally, if big N is congruent to 3 mod 4, then I to the minus n is I, and we have 1 plus I squared, that's 2I, we get -2 again. Let's combine the results to obtain the algebraic multiplicity of I. Our 4 cases, so n now is 0 or 1 or 2 or 3 modulo 4. If 0, we get 1/4, there is always 1/4, and then we have n from here, and from here we have -2, and then from here we have also -2, so this is -4. If n is divisible by 4, the algebraic multiplicity of the eigenvalue I is n divided by 4 minus 1. If n is congruent to 1 modulo 4, then we always have this 1/4, and we always have this n. Now n is odd, so we have from here, we have -1. And from here we have 0. That's it. So n minus 1 divided by 4. Then we have 1/4. If n is congruent to 2 modulo 4, we have our n. Then we have -2, and we have a 0 here. That's it. Finally, if n is congruent to 3 modulo 4, then we have 1/4. We have n. Now 3 is odd, so we take this -1. And we also have this -2. So we get n minus 3 divided by 4. It is a nice exercise to do the same for the remaining 2 eigenvalues, -1 and -I. For -1, you can use the matrix 1/4, and then we have identity minus f plus f squared minus f cubed. And for the eigenvalue -I, the matrix is 1/4, and the 4 matrices that we add together are identity plus I times f minus f squared minus I times f cubed.